Today I'd like to talk about rotational work and energy. The first thing I'd like to do is derive an equation for rotational work. We know that work is force through a distance. I would like to try to relate that to a torque through an angular displacement. So I'm going to start with the definition of work, force through the distance. And I know that this distance is the arc length, so I can actually replace it with r times the angular displacement and make this substitution. I also know that this force is involved in a torque. Torque is equal to force times the lever arm, or R. So I can then make this substitution. I can take force and replace it with torque over the lever arm. The two R's cancel out, and you're left with the definition of rotational work. Torque times the angular displacement. And here's the formal definition of it. Rotational work done by a constant torque in turning an object through an angle is torque times angular displacement. And this angular displacement must be in radians, and the work is in joules. Alright, so now let's derive an equation for rotational kinetic energy. Here is linear kinetic energy, where it's 1/2 mass times the velocity tangential squared. And I know that velocity tangential can be replaced with r omega, its angular equivalent. So now I have this equation. And I should be able to recognize that mr squared is the moment of inertia for a point mass. So now I have the kinetic energy rotational, where not only does it depend on the mass, but how that mass is distributed, or the moment of inertia. And remember, on the test, they'll give you different moments of inertia. And it also is related to the velocity, but this time the velocity is the rotational velocity squared. And here is the same equation, but this time a little bit more formally. The rotational kinetic energy of a rigid rotating object is, as I just stated, 1/2 I omega squared. And the angular speed must be in radians per second. And once again, the energy comes out to be in joules. Alright, so let's try a little conceptual problem. You have a solid cylinder and a hollow cylinder. They both have mass and a radius, and they start at the same exact height, so they'll have potential energy on top, and they'll roll down. They'll have energy on the bottom. They'll have translational kinetic energy and rotational kinetic energy when they reach the bottom. So we would like to know which one will have the greatest translational speed upon reaching the bottom. Well, we know that all the different types of energy it could have. It could have translational kinetic energy, rotational kinetic energy, and potential. And using conservation of energy, whatever you have finally had to be equal to whatever you had initially. And that's true for both the solid and the hollow cylinder. But on the bottom, you have no more height, so this drops out. And on the top, you weren't moving, so this drops out and this drops out. So you're really reduced down to this, where the final energy is either translational or rotational, and that was equal to the potential energy you started with. So there's the two equations again. And really, it's not that hard to understand. The one that will have the greater translational kinetic energy on the bottom has to be the one that has the smallest I. By having a smaller I, you're going to have more of your energy stored as translational and less of it as rotational. If you look at the hollow cylinder has a very high I compared to the solid cylinder. As a matter of fact, if they were the same radius and same mass, it would have twice the I as the solid does. So most of its energy, kinetic energy on the bottom, will be stored in rotational kinetic energy, while the solid cylinder will have most of it in translational kinetic energy. And I could prove it to you mathematically as well, but it's more important that you understand the concept behind it. And we'll do some examples of this in class as well.